everybody. Today we're going to be finishing up section 1 of chapter 2 on describing motion. Now, we've already looked at how to calculate constant speed. So we're going to do a couple of things here today. We're going to look at two other types of speed and another way to describe motion, okay? So, first off, let's talk about a type of speed that's not constant. Speed that's not constant means it's changing over a period of time. It's increasing or decreasing, and it can increase smoothly, it can decrease smoothly, it can increase and jump around, it can increase real quickly and then decrease the next second. So all sorts of different types of speeds. It's just not constant speed. Well, when you have a speed that changes over a period of time, then you got a little problem. You can't just take a particular distance and divide by the time for one leg of the trip. You've got to look at the whole thing in such a case. Now, an example. If you've ever been in your parents' car and say you've driven from out here on Manatee Avenue near the school, and you've driven out to the island, or maybe you've driven out to the interstate, one way or the other. You know that because of all the red lights and the snowbirds that poke along and take forever to turn off the road, you know that you cannot travel a constant speed on Manatee Avenue or State Road 64. It's not possible. So your speed is going to increase when you are at a light and it changes green and you start from rest, and you're going to increase your speed. It decreases when you see another light turn red up ahead, or somebody puts on their turn signal in front of you and you have to slow down so they can turn off the road. But what we can do is we can look at your average speed for the trip. Okay? For example, if you had somebody, or if your mom was driving you out to the island, say, you could sit there with a notebook and you could look at the speedometer every second and write down the speed that you're traveling every second until you get out to the island and stop. In such a case, you would end up with probably hundreds of different speeds, but you could also find the average of all those speeds for your trip. Now, finding an average is just like you do if you have several test grades and you want to find your average test grade. You simply add them all up and divide by the number of items added. So that's what you would do with average speed. You'd add up all those hundreds of speeds and divide by the number that you added together. Here's only one problem. That would be a big pain in the butt when you've got hundreds of different speeds to average together. So a different way of finding average speed, which works just as well and is a lot easier, is this. To find the average speed, S sub average, you would take the total distance you traveled from here out to the island, and you would divide it by the total time it took. Okay? All right, so the total distance divided by the total time. Basically, it's pretty much the same as constant speed, but you just simply have to remember that during that time period, the speed is not really constant. It is changing. The units are even the same. Meters divided by seconds, or meters per second. Okay? Now, sometimes when we're talking about speed, we don't want to look at a period of time. We want to look at one particular point or instant in time. And in such a case, you're looking at your instantaneous speed. Your speed at an instant in time. In fact, if you'll think about it, when you look at the speedometer on your car, it's giving you your instantaneous speed. At the instant you look at it, you see how fast you're traveling at that instant. If you look at it again at a different point in time, you get your instantaneous speed for that point. Okay? Now, so you can have constant speed, you can have average speed for a time period, you can have instantaneous speed for a particular point in time. All right, so now let's move on. Let's take a look at another way we can describe motion, okay? And that is with a graph. We can actually use a graph to describe motion. And specifically, we're going to do a distance versus time graph, okay? A distance versus time graph. Now, this is pretty particular, so pay attention. Notice that on a distance time graph, the distance goes on the y-axis, the time goes on the x-axis. Now, why? Why do we do it that way? Well, time is always independent. Nothing affects time. You can simply choose points in time at which to see how far the object has gone. So time, being an independent variable, goes on the x-axis because the independent variable always goes on the x-axis. The distance goes on the y-axis because it is the dependent variable. The distance traveled by the object depends on which point in time you're going to look at it. So for example, at 2 seconds, the distance was 20. But if we choose to look at 4 seconds, the distance was 40. So the distance depended on the point in time we looked at. So because it's the dependent variable, it goes on the y-axis. Now, once you have a graph of points in time and how far you were at that point in time, and you connect all the little points with a line, then you have a distance versus time graph. Now, there is a particular item I want to talk about on a distance time graph that gives us information, and that is the slope of the graph line. The slope of the graph line. Now, what does that mean? Well, look at these 3 graph lines here. They're very different. This one is very low next to the horizontal axis. This one's a little higher up, and this one is even higher. In fact, we could look at this as the steepness, okay? This is not very steep, but this, like little hills you're going to walk up. This one's not very steep. This is much steeper, and this is the steepest of all, okay? So the slope is defined as the steepness of the graph line. And here, because this is a distance versus time graph, it has physical meaning. Let's see if we can figure out what that is. Well, first, let's understand that slope is a mathematical quantity. We can actually determine the steepness of the line. In math class, they're going to teach you that slope is the rise divided by the run. Now, what does that mean? Well, if you don't know, I'm about to show you, okay? Notice that from the origin to the end of each line, you rise so far in the along the y-axis. This one you rise the most, and on this one you don't rise as far, and this one you rise the least. So this one, the blue line rises 10, the green line rises 20, and the red line rises 60. That's the rise. It's the change in the y value from one point to another. The run is along the x-axis. It's how far this way you go between 2 points. So it's the change in the x values. For all of these, the change was from 0 to 6, unless you pick a different point on the line. So rise over run is going to be the change in the y divided by the change in the x between 2 points. So that means you got to pick 2 points, okay? Now, usually some of the most convenient points are the origin if the line does go through the origin. If it doesn't go through the origin, you can't use that. And a lot of times the point at the very end, like this, okay? Then what you're going to do is you're going to use those 2 points to find the slope. Here's what we do. First, we get the 2 points. This one's 0, 0, x, y. This is 6 for the x and 60 for the y. So 6, 60. Now, the rise over run actually has a formula. We find the change in the rise, so that would be from 0 to 60. Frankly, you'd actually do it this way. y2 minus y1. y2 minus y1 over the run, x2 minus x1. Look right here, x2 minus x1. And that is going to give you the slope of the graph when you subtract the top and bottom and then divide them. Okay. Now, we're going to look mathematically more at that on a different day this week, and I'll have some examples and a little video of the examples and how to do it. It's actually pretty easy, guys. You're going to like it. What does the slope mean? Why do we care about how steep the line is? Well, there's a reason. Watch this. Let's look at the units involved that we're measuring here. The rise is the distance, so it's measured in meters. The run is the time. It's measured in seconds. So whatever numbers you have on top, they're going to be in units of meters. Whatever numbers you have on the bottom, it's going to be in units of seconds. Oh, and look, we're dividing meters by seconds. So we get units of meters per second. And what do meters per second measure? They measure speed. So the slope of a distance time graph is the speed of the object. Now, that also brings us to one more idea. How can we compare the speeds of objects on this graph? Well, the steeper the slope, the larger the speed value is going to be. Let's write that down, okay? The steeper the slope, the larger, or let's say, the larger the speed will be. Okay, the steeper the slope, the larger the speed will be. So look at the blue line. It's not very steep compared to the red or even the green. So the object that is being described, whose motion is being described by the blue line, is traveling fairly slowly. Okay? The object whose motion is described by the green line, that object is traveling faster than the blue line. And the object that's being described by the red line, that's the one that's moving the fastest because it has the highest slope, the biggest or steepest line. Okay? So, slow, I should have said fastest right there, not faster. Let's change that. Fastest of the three. So slow, faster, and the fastest. So you can easily compare objects and how fast they're going simply by looking at the steepness of the line. The steeper the slope, the faster the object is moving. Okay? Now, let's look at some other lines on a distance versus time graph that we can interpret. Look at this. There's several different things going on in these three descriptions. I've got a red line, a blue line, and a green line again. But notice they're very different. So let's see what these types of graphs are telling us, okay? And you get the idea just by reading what's on there. Whenever you have a straight line that has slope, it has steepness, even if it's negative steepness, okay? That straight line means constant speed. So a straight line that is not flat means the object has constant speed. And as we just saw, the steeper the slope, the faster that constant speed is. So this object is moving very fast and it's constant. They use the word steady, but I prefer the word constant, okay? So we could just put constant right there instead of steady. How about that? Okay, same for right here. Okay, this one, in this object that follows this path of motion, it's got a constant velocity right here too, but it's not as large as the blue line. Okay, but it is constant. Now, if you have a line that is a straight line that is flat, like this one, it has no steepness, it's flat. Flat means no steepness. This is an object that does not change location. Look over here on the y-axis. At every point in time, the distance, its location, stays constant or it stays the same. So it's not moving anywhere, is it? No, it's not going anywhere. It hasn't moved up or down the y-axis. So right here, you're stationary. You're at rest, okay? You have no speed, so you're at rest if it's a flat line. Okay, what if the line is not straight at all? What if it's a curve? Well, look at this. Right here, you have an upward curve. It curves upward. In other words, you're going from flatter to steeper. Think about walking up this hill. It's going to be fairly easy at first, but it's going to get harder and harder to walk up this hill because it's getting steeper and steeper. Well, if it's getting steeper and steeper, that means you're going faster and faster. So for an upward curve, okay, an increasing slope, that's what an upward curve is. An increasing slope is an increasing speed. You're speeding up. You're going faster. You start out slower and you get faster because it's steeper and steeper. Now, what if you have a downward curve instead of an upward curve? Well, let's look. There's no downward curve on here, so let's draw one. Let's suppose you have a curve that looks like this. It's sort of like the mirror image, isn't it? Okay? You're kind of flipping that one down so that it curves over this way. So it starts out steeper. It's harder right here to walk up this little hill, but as you get near the top where it flattens out, it gets easier and easier to walk along. So it's starting steeper, it's getting flatter. So you're starting out faster, then you're getting slower. You're slowing down. So a decreasing slope means a decreasing speed. Okay? All right, so constant speed here, here, and even here. You're just going back the other way. No speed where it's flat. Increasing speed where it gets steeper. And decreasing speed when it gets flatter. Okay? All right, and we will be practicing using this kind of interpretation, I think, tomorrow. So, see you then. All right? Bye-bye.